So this video is on what is termed a heating curve. What a heating curve does is it describes what happens to a pure substance as heat is added at a constant rate, which is up here in my little quick definition. What you want to look at as you would like to look at the axes, and what you have over here on the x-axis is you have time. On the y-axis you have temperature in degrees Celsius. Now, at the lowest temperature, which is at point A, we can assume we have a solid, and then at some point we have a liquid, and then here we have a gas. So the S, L, and G stand for solid, liquid, and gas. Let's talk about the different line segments here. On segment A-B, what we can see is as time passes, okay, and heat is being added, okay, the temperature increases. And this means on that diagonal segment, okay, therefore, 3 dots, the kinetic energy is increasing. So whenever you see a diagonal segment going up as time passes, that means that the particles are moving on average faster, because temperature is average kinetic energy. And as we get to point B, which is at 50 degrees as opposed to 10 degrees, our start point, clearly the particles at 50 degrees Celsius have more kinetic energy than those at 10. And then what's interesting is you see this leveling off on segment B-C. Now you're still adding heat, and matter of fact, it only took 2 minutes to raise the temperature by 40 degrees, but it takes 3 minutes to get it from point B to point C. And at that point, we see the graph plateauing. Now, the easy way to remember this is whenever you see a plateau, what you're seeing a phase change. And what's happening is at this temperature, and this is the odd thing, okay? The odd thing is that we're starting as a pure solid at 50 degrees, and by the time we're done, we're in pure liquid at 50 degrees. During that entire time, there's no change in temperature. And what this means is both the solid and liquid phases of matter can exist at the same temperature. And that also means that the kinetic energy is not changing. So during the phase change, there's no change in kinetic energy. Well, where's the energy going? It can't just disappear magically. Well, as the particles gain more degrees of movement, so they kind of unstick from each other, because now we're going to a liquid where the particles can sort of rotate around each other, right? As we go from point B to point C, what's happening now is that we say that they now have more potential energy. So while there's no change in kinetic energy, during a phase change on one of these plateaus, there will be a change in potential energy. And since we're adding heat, we're going to see an increase in potential energy. And that makes sense because we're going from a solid to a liquid. So easy way to remember, wherever there's a phase change, there's going to be a change in potential energy. No change in kinetic energy. And that will always be a plateau on the diagram to help you sort of remember it. I hope I'm spelling plateau correctly. All right, in the next segment, which is from C to D, we once again see the change in kinetic energy, because once again we see a change in temperature. Now we have just liquid, right? As soon as we have all liquid, it starts going up again. But not until the last teeny tiny bit of the solid is completely melted. And since the temperature is going up again, therefore, we have an increase in kinetic energy. And while there's a change in kinetic energy, there's no change in potential energy. So, no change in potential energy. So whenever there's a change in one, there's not a change in the other, at least during these phase changes. From D to E, we see the plateau again. I'm not going to repeat everything, but we should know at this point, whereas back here this was fusion, right? This other plateau is going to be vaporization. And specifically, it will be boiling, because this is going to happen at the boiling temperature of the liquid. And during this change, we're going to start off as all liquid, but by the end of it, we're going to be all gas. And again, we're going to have the same little diagonal box. Slowly but surely, all that liquid turns into a gas. No change in temperature. So once again, we see that we're absorbing energy. And since there's no change in temperature, there's no change in kinetic energy. But because this is a phase change, we're going to see a change in potential energy. And in this case, okay, therefore, the potential energy is changing, and it's going to increase. And again, on the final segment here, which is E to F, right, we're again going to see an increase in temperature, therefore an increase in kinetic energy, and no change in potential energy. The opposite of a heating curve is a cooling curve. In a cooling curve, well, I tried to make this one a mirror image of the heating curve, but I'm not the greatest artist, and This is not the best medium for that. But what I want you to note is, at the highest temperature, instead, right, to the left now, since this is going to be time again, right, and this is going to be degrees Celsius, temperature in degrees Celsius, here we're starting off in the cooling curve at the highest temperature. So instead of starting off as a solid, at the high temperature, we're going to start off as a gas, and this would be a liquid, and this would be a solid. And some of the same stuff is happening. One of the things you want to know is the temperature at which this phase change right here happens, right? The first of the two phase changes right there, at which a gas goes back to a liquid, which is condensation, okay, is 110 degrees Celsius, right? Which is the exact same temperature as the boiling point. Essentially, if you're at 110 degrees, if you add heat, whatever liquid you have will turn into a gas. If you remove heat, whatever gas you have will turn into a liquid. The boiling point temperature and the condensation point temperature are exactly the same. So 110 is both the condensation point, okay, but it's also equal to the boiling point of the liquid. They're exactly the same thing. And the same amount of energy you put into melting, into boiling, will be the same amount of energy that comes out when it condenses. So no energy is magically created. Now, in terms of energy changes, whenever you have diagonal, right, so if this is, we're going to call this segment A, we'll call this segment B, we'll call this segment C, this D, and this E. Segment A, right, because it's a cooling curve, we're losing energy, the temperature is going down. On segment A, we're going to have a decrease in kinetic energy. On segment B, we're going to have a decrease in potential energy. Notice they're all going to be down hours because we're losing energy now, right? And again, on the plateau, we're once again seeing a phase change, and we're seeing that potential energy is changing, but this time it's decreasing. Whereas in the heating curve, the potential energy on the plateau would be increasing. Segment C, temperature is going down, so we have a decrease in kinetic energy. D, potential energy is going down. And this phase change, and now notice the temperature, okay? This is happening at 50 degrees Celsius. That was the melting point temperature of the previous substance on the previous slide. It's also, okay, the freezing point. So the freezing point is equal to the the melting point. They're the same exact temperature. And of course in segment E we have temperature going down, so the kinetic energy is decreasing. So we can assume the lowest kinetic energy, okay, is going to be associated with the lowest kinetic energy will be either solid or a liquid. It will be a solid because down here we have the lowest kinetic energy. The highest possible kinetic energy would be a gas. Although it is possible for a liquid and a solid to have the same amount of kinetic energy because they can be at the same temperature. Okay, so this covers the basics of the cooling and heating curve. On the next video, I'm going to show how you can use this to quantify and determine something called the heat of fusion and the heat of vaporization, etc., by using data from the heating curve or the cooling curve.